difference algebraic proof is finitely sigma percent. G is a sigma algebraic proof, then the coordinate ring of G is finitely. Yeah.
Please make the chart.
Okay, so because if we know this, then we know that here the right hand side is finitely sigma presented over the first over K, then we know that is true over L. Then so going to the left side, we know that this is finitely sigma presented over L, and then from the lemma we know that vector R has to be finitely sigma presented over. Okay, so this is how you can go from the group to the difference algebraic relations, and so this is like to put things into a bigger picture. So this is an example on how you can use results about difference algebraic groups to prove stuff about difference algebraic relations among solutions of linear differential equations. Okay, so I'm not sure on how much I should say on the proof of this theorem. So maybe I'll say a little bit on it, but maybe I'll also motivate the construction by discussing an invariant which is called the limit degree. So let me maybe first recall the limit degree of a field extension. So this is a very classical and important invariant in difference algebra. So let me first recall the definition for different field extensions. So if L over K is an extension of different fields, then so assume that L is finitely generated as a different field extension. So you can find some finite set B, such that B and all its iteratives under sigma generate L as a field extension. Then you can look at the following sequence of integers, or this value can also be infinite. But so when generating L as a different field, you look at applying powers of sigma to elements of B, and you can look at the degree of this field extension, where you here go up to the i's power of sigma, and here you only go to the I minus first power of sigma, and just call this degree of the field extension di. It might be infinite, but it might also be finite. And then one can show that if you take the limit as I goes to infinity of these integers, well, first of all, you can show that this limit exists. So it's either infinite or a positive integer. And then you can also show that this limit is independent of the choice of B. And this is called the limit degree. It, in some sense, is a measure for the size of the extension. Wow. But it's an important invariant for extension of difference field. It doesn't have a differential analog.
Well, it does. The number one.
Okay, it's always just one. Yeah, okay. Yeah, that's true. Okay. Yeah. Okay, and so the general philosophy of the sigma-Galois theory is that the important properties of the field extensions of L over K of the sigma-Picard-0 extension should be reflected as properties of the sigma Galois group. And so it's really natural to ask, first of all, what is the limit degree for a difference algebraic group? And of course, you want that the limit degree of the sigma Galois group is the same as the limit degree of the sigma Picard-Bessel extension. Okay, so we're asking for the limit degree of a difference algebraic group. So what is it? And also, of course, you would like to know that these two limit degrees are the same.
And the L is the Picard-Bessel extension?
Yeah, L over K is the sigma Picard-Bessel extension.
Okay.
Okay.
And in simple terms, what does it say about the relations among the solutions?
Well, knowing the limit degree,
So if the limit degree is infinite, then you have transformal transcendence,
yeah,
at least one. And if the limit degree is finite, then the sequence of DIs is obviously non-increasing, because whatever relation you had, it's still there.
so if the limit degree is 1, you know that L over K
Okay.
is finitely generated as a field extension,
And finitely
this-
presented too, right?
finitely presented.
Sure. Well, because once
Yeah.
you get DI, once dn is equal to 1, then actually, if
Then
you know where, here's what you really know. Once you know where the limit degree is attained, and it has to be attained somewhere, it's a non-increasing sequence of integers.
Yeah.
The moment it drops to an integer, you have only finitely many options. Where the limit degree is attained is the point past which you don't need to look to find generators of the ideal.
Which means what?
Ideal?
The orders.
Difference ideal.
Well,
the
it's
orders
not
about
quite.
The number of sigma transforms.
It's not quite. You're taking fields here.
Yeah.
Yeah, but actually, I mean, there's
I'm thinking
some.
that K is a field. And
Yeah,
that's
no,
fine.
There's some-
looking at few extension degrees, right? So what you're saying is the domain, right? I mean, you're looking at the polynomial ring generated by B and C prime B just now,
Yeah,
but this is the field.
But I think, like, at least philosophically, it's true what Alice is saying. So, like, if you want to compute the generators, and then if you know that, yeah. So at least for the sigma Picard-Bessel case, yeah. So if you want to compute the generators for the difference ideal, you have to look. So once you reach the point where the DIs become constant, you've got everything. Yeah, this is something one can show.
Meaning what? Whatever.
So okay, so
the algebraic ideal.
you know, so your ideal of difference algebraic relations which you're interested in, it will be generated as a difference ideal by difference polynomials of some order. And then if you cut your ideal, the original ideal, with difference polynomials of up to order m, then so you'll know there exists such an m. And actually the m from which those di's are constant is a good m. But it's hard to tell the m. It's basically impossible to tell the m. Yeah.
Another good use of the limit degree is that it's an invariant of all kinds of relatedness for different field extensions. So if you have, so say you have two different field extensions, you are given presentations of two different field extensions, and somehow you can compute their limit degrees, and they're different. Then there is no way they could be the same field extension in any sneaky fashion. Or
Yeah, the
they
limit
can't be
is
off of-
just a
they
really
can't be off of each other by an algebraic extension.
just a really important invariant. Like
It's a
it
really
has nice
invariant.
properties, like it's multiplicative in
Towers.
towers and stuff.
But its primary use is theoretical for some internal purposes.
I wouldn't say that.
Well, if theoretical is everything that isn't algorithmic, sure, why not?
No, people who would want to find relations would not ask about it. You might use it for your computation, your own computation, but it's not for other people to see, right?
No, I think it's like if you would know the limit degree of the sigma Picard-Bessel extension, Yeah, that's definitely a very helpful information. In particular, it tells you, as Sally said, in particular, it tells you something about the sigma transcendence degree, and it tells you something about the.
But there was rumor that there was no way to compute it.
There's no way to compute the M where it is
The M.
attained. But it may be.
I mean, it's really hard. Like if you are able to compute the M, you're done. Like finding the M is as hard as finding all the different algebraic relations, right? Because once you know the M, you can like compute all different you're done. So you know you can compute all different algebraic relations just by computing algebraic relations. Say if Rorschach's algorithm would be applicable still in that dimensions, you could do it in principle.
So M, you can find M in some cases. You know, if you sit down, maybe.
But if you get really lucky, you might be able to find M in some special cases. Yes.
But what I mean is, there is a hope. There is an algorithm actually that finds it for some limited sizes of equations, right?
I mean, what
Well,
are you given
like
when
for-
you can find M?
There's an algorithm.
Huh? What is given when you say you can
Oh,
find
a
M?
differential, a matrix.
Presentation for B.
Okay. All right. So you know B,
Or-
say, starting from B, you can find B.
Or like given A, like given given delta y equals AY, given A, right? I mean, just starting from there, given
That's
A.
different. That would be
And
different.
I think like for order 2, I wouldn't go and so for differential equations of order 2, I wouldn't go and try finding the M. I think you'd rather just try going through different algebraic subgroups of
Yeah.
GL2.
I like that better.
Yeah.
But then you'll find the M after that.
Yeah. Okay.
Yeah.
Once you know, once you know everything, you know the M.
Yeah. So you can find the M, and that will be through
Yeah.
doing something else.
Yeah.
Use the
By
groups.
elimination, right? You can find M by elimination.
Yeah, the subgroups.
But it's sort of, I mean, really M, also M is a very, very interesting invariant, yeah. Yeah, but, okay.
It's not clear that M is a variable. You're independent of capital B.
No, it's not.
Yeah, so maybe M is not,
No, M is not an invariant
yeah.
at all.
but it's sort of, yeah, like it depends on the embedding, if you want.
Yeah, yeah, yeah.
Yeah.
But while searching for that, wouldn't you find the DIs?
Oh, given the capital B, yes.
Yeah, yeah,
Not given A.
Given A, well, then it depends on your capital B. You know, for example, if I replace B, right, by the B comma sigma B, right, it will still work, right? It's
M
still-
will change, but D will
But
not.
yeah, but M would change, right?
Yes, M will
that's
change
right.
and the DIs will
It's the same
change, but then the
The
degree
DI
will
will
not.
change, right, sure.
And so in principle,
problems.
you can compute all the DIs. Yeah. For every I, you can compute DI.
Given
Yeah,
the-
using Rorschach's algorithm.
Yes.
Okay, in principle, I don't think it's very practical, but okay. And they are non-increasing, but you wouldn't know when they stop. Like I think it's so it's not true. Like if the 2 equals the 3, it's not true that the 4 is gonna be equal to the 3. So there's no easy way to check that sequence stabilizes.
That's right.
Yeah.
That's
Yeah.
yeah.
Okay, so let's go back to thinking about the limit degree of a difference algebraic group. And, well, so maybe the first, so since we already know how to do it for fields, you might think, okay, let's maybe just take the, something like the quotient field, that wouldn't work that well. Because the coordinate ring, it might not be an integral domain. And then you might want to take the connected component, but okay, that would actually not work that well either. So we need to do sort of something else. And so to define it here, we sort of chose, we needed to choose generators of the extension. And here what we need to do, so what we need to do is to choose an embedding into some algebraic group. So that's sort of the geometric analog of choosing generators is choosing an embedding So we need to embed T into an algebraic group, say into GLN, and so this is
I'm not quite interrupting you.
yeah.
I'm not quite sure that if, let's say, some di is infinity, right?
Yeah.
That from then on, it cannot be finite again.
So these are
They're
non-increasing, so they get smaller and
But
smaller.
once they drop, they never go back up. It may
Why?
drop later, and you might not know when it drops.
Why?
It's
Well, yeah, of course. For example, let's look at the equation sigma to the 17th of x equals x.
You might have coefficients. The thing
No,
is
no,
that-
but for 16 steps it's infinity, and from then on it's 1.
But you're not assuming that anything is of dimension 0. So in general, instead of looking at the degree, you should look at the transcendent degree, right? I mean, when you look at degree, you're thinking about something algebraic, actually.
Yes. So, for example, if
But then it may not be algebraic, right? So
In that case,
maybe
it's
at some
infinity
point you
forever.
introduce a sigma transcendental, but then after that, right, the relation would be just still, the degree would still be finite, because you could have an extension
Yeah.
which is transcendental, and then algebraic extension,
Algebraic over it.
and then transcendental extension.
Yeah.
no,
But
so
we're
that's
adding-
not
we're-
happening.
we're adding
That's not
sigmas
happening.
of pi.
That's not happening. You can prove that it's not happening.
Well, because if sigma to the 17th is algebraic over the previous 16, apply sigma to the relation, and then sigma to the 18th is algebraic over the previous ones, and apply sigma again, sigma to the
No, but it
19th.
depends on the choice of B.
Yes, but having made a choice of B, if there is some I for which di is finite, then from then on, di's are no bigger than this di for that particular B.
Right. But then before that, it could be infinity.
Yes,
Okay. So when you say limit as I go to infinity to y,
yes.
you're ignoring the infinite
No, it
possibility.
might be infinite.
It might be infinite.
I is going
It might be that
Okay,
all of them are infinite,
right.
and then
okay.
it's just infinite.
Right. But then if you start with infinite and you go to then finite, then you take the limit to be finite.
Oh, no.
Yeah. So once
And
it,
because
yeah.
after that, it will never become
Right.
infinite.
So,
Correct.
okay, fine. So in some sense, even if the extension is transcendental,
The first
sigma
one,
transcendental,
sigma transcendental, then at each step you will be adding transcendence degrees. And so then
What?
di will be infinite.
no, I have my transcendental already is in there already. I have a sigma. I mean, I have one variable which is sigma transcendental and
Okay,
another
let's,
one algebraic.
Let's wait for this for later. This is something I'm sure
Okay.
about and I'm happy to explain.
Okay, all right. So let's go back to the limit degree of different algebraic groups. And the first thing we need to know is that we can embed any different algebraic group into an algebraic group. So, and here, to be a bit more precise, let me add the word affine here, which is really important. So everything I've been discussing here is just affine in terms of difference equations. So all the difference varieties are affine difference varieties, and morphisms are given by difference polynomial maps. So any affine sigma algebraic group, they call it G again, can be embedded into some general linear group. Okay, so for some n, you can find an embedding, and so inside GLN, G is defined by a difference ideal. We call it I of G, so that's the defining ideal of G. So it lives inside the coordinate ring of GLN, which is sigma generated by an n times n matrix of sigma indeterminants, but you also need to invert the determinant. And so you can think of this as so of the coordinate ring of GLN as a directed union of just K algebras, not K sigma algebras, so where you just look at equations up to order I. So you look up to sigma I of z 1 over the determinant of sigma I of z. Okay, so these are finally generated K algebras. And
Is this a sigma embedding?
yeah, this is a sigma. So in this fact here, this is a sigma embedding. Yeah. So
Yeah.
if you want, this is an isomorphism of different algebraic groups. Yeah, it preserves whatever you hope it. You might hope it preserves. Okay. So but once we are inside GLN, then G is given by such an ideal, and so here, this is really the coordinate ring of GLN to the power I plus 1, because you start counting from 0 here. And if you intersect the defining ideal with this coordinate ring, so basically you're saying, okay, look at the defining equations of G up to order I, then this will define an algebraic subgroup which we call GI. So this is a subgroup of GLN I plus 1. Okay, so that's the group I've just defined. It's an algebraic group defined by the defining equations of the original difference algebraic group up to order I. This is what we call the ith order Zariski closure of G. So it's an algebraic group. So for each order, you have an algebraic group, and these groups is short. You might think of them as like as I increases, they contain more and more information on G. Like if you would know all GIs, then you would know the complete G, right? Because just if you think of in terms of defining equations, or once you know all the defining equations, you know G. So and these are, so the GIs are just algebraic groups, so they don't contain information about sigma, but the information about sigma can naturally be encoded by some map. So these GIs are connected by the following maps. So there is a projection from GI to GI minus 1, which simply drops the last coordinate. So G0 to GI are n by n invertible matrices here. Okay, we're living in GL n to the power I plus 1 here, and then we're projecting into GL n to the power I. So we drop the last coordinate. So here this should be clear that this is a well-defined map. So if these matrices satisfy all relations up to order I, then the first entries will satisfy all relations up to order I minus 1. Okay, so that's obvious. And we also have a map which is sort of encoding the difference structure. And this one is a bit more interesting. So it almost looks.
So it's a matrix. The G, small g's are actually matrix with the determinant.
These are. So this is really a subgroup of GLN to the power I. So these are matrices. These are invertible matrices. Yeah.
I'm just thinking about your projections because the the algebra coordinate ring,
Mhm.
has the one over determinant and one
Yeah.
sigma determinant. So your G0, for example, should be G0 and 1 over determinant G0, right?
Yeah, I mean, having the determinant here, like the one over the determinant, makes it invertible.
It
But
doesn't
so
do,
really,
it doesn't do anything.
we don't have
I know,
to write the coordinates for the determinant, really, right? Okay, and so that also is, if you do the projection such that you forget the first coordinate, so you go here from G1 to Gi, then you don't quite land in Gi minus 1, but you land in what we call the sigma twist of Gi minus 1, which means that you take the defining equations and just apply sigma to the defining equations. Yeah.
By the way, for people who were here, I guess last week when I was talking, this is exactly the same construction.
Okay. So maybe let's take a minute to think why this is well defined. So here, this tuple satisfies all difference algebraic relations up to order I, and then we forget the G0, and we ask, okay, so which relations are then satisfied by these, and so this is coming from the fact that so when you have relations, say of order I minus 1 here, and then you apply the sigma to this relation, they will still stay relations, because the defining ideal is a difference ideal. Okay, and applying sigma to the defining equation means that you have to apply sigma to the coefficients of the equation. Okay, and so this is why you get the sigma twist here. Okay, and so there's a commutative diagram relating these things, and maybe so I don't have to draw maybe. I don't know how are we doing in time. Maybe I should finish in like 5 minutes, or you still good?
I don't think there's any upper limit.
Okay. 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 So there's
Midnight.
a commutative diagram relating these maps. So going down, we have the sigma I here, and we have, I'm going to I minus 2 here, we have the sigma I minus 2 here, here we have the pi I, and so the thing we can have here is pi I minus 1, but with the sigma twist as well. And so you see that this is commutative, because if you go here or here, what you do from the original tuple, you just delete the first and the last entry. Okay. So this is commutative, and now if you define Gi to be the kernel of pi I, you find, okay, so if you have something in the kernel of pi I, so it goes to 1 here, then it has to go to something which is in the kernel here, but the kernel here is really just sigma of the kernel of pi I minus 1. So this means that sigma I induces a map from Gi to sigma Gi minus 1. Okay, so sigma Gi minus 1 is the kernel here, and so sigma I has to map the kernel into that kernel. Okay, and now what you can prove is that these sigma i's, so in general, these are closed embeddings. And actually, so for I big enough, these are isomorphisms. And isomorphisms, or maybe and for I big enough, these are isomorphisms. And this is really similar. This is so the analogy to what we were discussing about the limit degree before is that the difference of the di's is non-increasing, and well, what you can find from the fact that this is a closed embedding is you find that if you say di is just the size of Gi, then you find, so the size is really just, like you hope it's a finite group, that it's the number of its elements, and maybe more abstractly, it's the dimension of the coordinate ring as a k-vector space. So, as these are closed embeddings, so you shouldn't be so surprised that it seems like a very strong condition, like this group is finite, but it also was a very strong condition that the di's are finite, right? Like this was an extension of finite degree. If we wanted to have a group in GLN,
Okay.
and then we constructed those GIs,
so
we constructed those Taritsky closures.
Okay, so here's what
And
I'm
then-
going to start with. I'm going to start with the group defined by x squared is equal to
Just one, I hope you're just
No.
saying one, no?
sigma of x,
X squared. Okay.
sigma of x cubed,
Cube,
cubed, not squared.
sigma squared
No.
of G, what do you mean?
Sigma,
Oh,
sigma
cube.
of g is a quantity cubed,
Cube.
multiplied by itself 3 times.
Okay.
So I don't think you're ever going to have embeddings. This will always be a 2 to 3 correspondence, 2 to 3.
Okay, so
2 to 3,
I think I can.
and nothing will ever cancel.
Okay, so let me write it the way I would write it. Okay, so this is all G squared
2 minus third equals 1. Yeah.
is
1.
1. Yeah.
I mean, this was limit degree 3 and inverse limit degree 2, or vice versa.
you're saying it should have, yeah. So I would say this has limit degree 3.
Sure.
Yeah.
So
So you
because
think
that will never be.
the GIs should all be just cyclic groups of order 3.
Wait, who
Those.
curly GIs?
Those are the, yeah, so here,
Kernel.
yeah, so here, this
the
is the,
kernel.
They're kernel.
Oh, I see. I'm sorry. I missed the straight G's to curly G's.
yeah, yeah.
Fraktur.
Yeah, these are like never gonna, like almost never gonna be isomorphic.
Yeah. Okay.
Yeah,
Okay.
but on the kernels, the sigma i's are gonna be eventually isomorphic. I can say something else in terms, just let me say something in terms of the pi i's alone, okay?
Yeah. Okay.
So without worrying about the clotted GIs.
Okay.
And what you can say is that really, so you can say that the degree of the GIs is not increasing.
Yeah.
This is what you can.
Yeah.
So so really the degree of the pi i's is really just the size of GI, right?
GI.
I mean, so it's sort of.
Yeah. Okay.
So for morphisms of algebraic groups, it's easy to define the degree. You can just take the size of any fiber, because so you know all the fibers have the same size for morphisms of algebraic groups. But so if you have morphism, so this is sort of the obstruction to defining the limit degree for sort of more general difference varieties, is that you like if they're not being defined by a transformally prime difference ideal, this is sort of not so clear how to do it. But this is why you can do it for groups, because all the fibers have the same size, and this sort of then is really helpful.
So in the case when the curly G's are finite, what does closed embedding mean, other than injection?
Yeah, if you want to think like, yeah, okay.
Or I mean.
Well, actually, so this really works just for like over any field, and the groups don't need to be reduced. Say like you can have, yeah. No, it's actually really
Yeah.
it works very nicely.
Yeah, okay.
Like in that generality, sort of, and like the way you do it, like with the factorial approach, you don't ever have to make that face, really. It's really just it's very natural. You never get into the details of worrying about something not being reduced or something. It's just more like the scheme theory formalism.
Exactly.
But it's like, with the factor of points, you don't really,
So you really are sort of following from the sigma I, the left-hand side of the diagram being closed. Now down below.
Yeah.
There.
So this I don't think so. Sigma I in general will not be a closed embedding, but only like the restriction to the kernels will be a closed embedding.
But the fibers everywhere really are that. Right? Because if I take 0 in the left-hand corner here, fiber over that is,
No, it's kernel pi I, not kernel sigma
yeah,
I.
sorry. The map on the kernel pi I to kernel of sigma pi I is the one that's going to be a closed embedding.
That's not the kernel of sigma. That's not sigma of the kernel of pi I. That's sigma of the kernel of pi I minus 1.
Yeah, but you're just spreading it out, aren't you?
Yeah, so no, my feeling is like this is sort of, it's very crucial to have this restriction to the GIs, really. And so sort of so the GI really controls what is really controls the equations which you need to add to go from order I minus 1 to order I, sort of. And yeah, so let me maybe finish up here on the definition of the limit degree. So this is, you can define it as the, yeah, I'm sorry about this. So as the limit of, so as I goes to infinity. So knowing that these are closed embeddings, you know that this sequence of integers is non-increasing, and so you know that this sequence stabilizes, and so the limit exists, and you can show that it does not depend on the embedding of g into gln, which we chose at the very start. Okay. And there's a lot of nice properties you can prove about the limit degree, like for example the limit degree, like the analog of the limit degree being multiplicative in towers is that the limit degree of the quotient is the limit degree of g divided by the limit degree of n. So that's stuff like that. And okay, so going back, so maybe in the last 2 minutes, coming back for the to the difference algebraic relations, let me just say then the statement we already discussed briefly before. So if for m such that the sigma I restricted to gi is an isomorphism for I greater than or equal to m, then the defining ideal of G will be generated by IG. Yeah, maybe let's just try by the, yeah, it will be generated by the equations of order n.
By the
And you can go. Oh yeah. Okay. By the. Yeah. Okay. And you can take the same m for generating the ideal of different algebraic relations among the solution of the linear differential equation. Because, okay. Yeah, and of course you can then, because you really so going between the equations and going between the defining equations of G and the difference algebraic relations is sort of compatible with the order, and then it's not hard to see that also the limit degree of L over K is the same as the limit degree of G. And I think I'll stop there.
To go back to the definition of is it okay to ask question?
Sure.
Of pi I from your codes from your actually from the group GI, G bracket I, G bracket I minus. Now suppose the equation that defines capital G, right? Does not involve G itself. So say take the push it up a square equal to sigma square of G cubed.
So sigma of G squared equals
sigma of G, sigma square of G
cubed.
Everything cubed.
Cube.
All right. Suppose that. So now, how does pi I and your how does pi I work? Let's say for I equals to 3 or something.
We're looking at the solutions in fields, so we might as well assume that sigma is inversive. This is exactly the same as my example.
No, not in the projections, not in the way that you're projecting, right? I mean, you're projecting, you're writing so I have a G0, G1, G2, let's say, all right?
But any
Oh, yeah, so
And I want to project it to,
But he's taking the heuristic closure of the set of solutions of that equation, and if you're taking solutions of that equation, then if you're taking solutions from fields, they will all also satisfy my equation.
Yeah, but so here, I mean, so I would not do that. Like for me,
Okay.
that is definitely a different group than this one. Okay. But it's like it's really just like shifted. I mean, understanding that example and understanding that example is pretty much equivalent. But it's still different groups. But so okay, so I mean we can try to we can try to do all GIs. I mean
Yeah,
it's
that would be helpful.
right.
I mean, just explicit writing out
Yeah.
what satisfies what.
Yeah. Okay. So there's no okay. So let's the first thing is G0, right?
Okay.
So algebraic relations just for G, there's none, right? Okay, so G0 is like GN1, right? Okay, so how about G1? Okay, so what is
Let's do GM first, GM then.
G1 is really okay. There's no nothing here. And then I guess for 2, yeah, we get something for 2, right?
Right.
Okay, so this is a subgroup in Gn cubed, and okay, so it's gonna be G0, G1, G3.
G2.
Oh, yeah, thanks. G2. So we don't have anything really for.
Yeah.
So this like
G1
becomes
square equals
G1, like this is
G2, right?
G2,
Right.
then it is
G1 square equals
G1 squared equals
G2 cube.
G2 cubed.
All right.
Okay, so this is in
G up.
G cubed.
Now let's look at the maps and let's see what they are.
Yeah, start there.
And then you look at the kernel.
Okay, so the PIs are just that projections onto the first factors, right?
Let's look at G1 to G0.
Do you want to do G0, we'll have infinite kernel.
So
Oh, sorry.
G1.
G1. So the first kernel is just a GM. Then the what is gonna be the G2. So this is the kernel of the second projection. So what is the
we go to G0, G1.
Which is all the base in G2.
we just put G1 equals 1, right? So it's just gonna be G2, 3 equals 1.
No.
Oh, the kernel, yes.
So the kernel, so really all you have to do is just put the 1. I mean, so what is by I is just a projection onto the first coordinates.
Yeah.
So the kernel is just if you just put a 1 here. Like kernel means mapping to 1. So put the 1 here, put the 1 here, you get G2.
Okay. All right. Okay.
Okay, so we are already at 3, and this is what you actually expect for the limit degree. But okay, so I mean it gets more interesting. Like if you have so for G3, you would have 2 equations, right? So for G3, you would have this equation and apply sigma to this equation.
Yeah.
Yeah. but then setting everything equal to 1, other than the last coordinate, will always just give you that cube equals 1.
Right.
Right?
P3 cube equals 1.
Yeah. So this is really really all you get is this equation in the end.
Right.
Like for all the higher i's. And if you would have done Alice's example, you would have just gotten that at one step earlier, sort of. Like there would have not been this GM, right? There would have been the G cubed equals 1 right away.
Well, the thing is, in G1, it's transcendental. I mean, that's transcendental
Yeah.
degree 1.
Yes.
So you. Well, anyway, I'll go home and work it out.
I mean, notice that in the proposition it's for I greater than 1.
Yeah, I know.
It's an eventually
Right.
this occurs.
I mean, the way that it looks like, of course, you're using just degree of fields.
Yeah.
But in general, we would use transcendent degree, and we would have what might be called a different dimension polynomial, right?
Yeah.
Yeah, there's an analog for that. And so the thing is
you're not
that
assuming anything about different dimension 0 or anything like that, right?
no. So that
That's why I don't understand why you can work with just degrees, which is.
so okay, I mean
Because we're willing to leave the transcendental case as saying infinity and not distinguish between transformal transcendence 1 and transformal transcendence 2. This is a degree, not a dimension.
I mean, there's various things you can do, and there's some sort of different. So I mean, we call it we have just one endomorphism. So the dimension polynomial is sort of just linear, and here is. So this is what you can prove is that for I big enough,
Yeah.
there exist integers d and so actually non-negative integers d and e, such that you have this equality. And D is the sigma dimension. So actually it's not completely obvious how to define the sigma dimension of a difference algebraic group. And actually that's how I defined it, showing that it does not depend on the embedding.
Oh.
And
Yes.
okay, and there's this E, which is also an interesting invariant, but it depends on the embedding.
Yeah.
It does depend on the
Yeah.
embedding.
Same as the dimension polynomial.
Yeah.